Hi, I'm Etta Spencer. I'm in Toronto, and we're going to go to Turin. No, we're going to Milan, Italy, which I haven't been to in a long time. And we're going to meet with Peter Wadhams, who's there to do some research. And we're also going to go to Ottawa, where Paul Beckwith is walking along the street. Actually, it's rather a pleasant image of you. I mean, you know, it's kind of fun to see you walking along, and he's going to find a quieter place to sit and talk to us where there won't be street noise. So that's very nice. And we're going to talk, I'm not quite sure, but these guys are both climatologists, real experts in their area. And I had almost given up that Paul was going to be with us. So poor Peter was going to have to wing it, giving an impromptu lecture just to me. And I'm a pretty bad interlocutor on things like Arctic sea ice. But Peter, we're gonna talk a little while until until Paul finds a place to sit down. And in the meantime, you can tell us what you're doing research on, or what's on your mind lately. What are the issues that are that trouble a? Well, I know you told me you didn't get any funding to do research on chimneys, and since I didn't know what chimneys were, that was very distressing to me to think that you weren't getting your funding to study chimneys. Why don't you explain first to our listeners what a chimney is and why we should be looking out for the changes in chimneys?
Well, there's a problem is that in the world is that there's a circulation system called thermohaline circulation, which is not the normal circulation of water on the planet, which is mainly driven by the wind, but it's driven by changes of salinity and temperature, and it's a very slow circulation. But it was called the ocean conveyor belt by its discoverer because it's slow, but it's inexorable. It goes. You have a current system on the ocean's surface, and then you have sinking places where the water sinks down to the deep ocean, flows along the deep ocean bed, comes up again in other parts of the world. And this is really important for driving a lot of phenomena, including the transfer of heat and the transfer of ice in the case of the Arctic.
Now, wait a minute. Is this just in the Atlantic, or is there something similar in the Pacific?
Well, it's worldwide, and but the important places really are where the water's sinking, and those are very small in number. There's only about 4 of those places, and one of them is in the North Atlantic in the Greenland Sea, and that's the most important one.
And so that's a chimney.
That's a chimney, yes. The water sinks, and it doesn't just sink as a kind of a mass of water. It sinks it in the form of narrow rotating cylinders, a bit like water going out a plug hole of a bath. And one of those is in the Greenland Sea, another one is in the Labrador Sea, and the rest are in the Antarctic. So the one in the Greenland Sea is really important, and it happens where there's ice forming, and the ice is becoming more dense because of salt. As the ice forms, salt is deposited in the ocean and makes the ocean more dense. And that's a region called the Odden Ice Tongue, which was very famous because it was studied a lot we were the ones who were studying it a lot, but other people did as well. And this was really believed to be a key place in the world ocean, this Odden Ice Tongue. It was discovered in the 19th century by Norwegian sealers because seals would come out on the ice there and have their young. So we studied it, and it's been studied by others. And then suddenly it stopped forming. And that was maybe about about the early part of this century, and you didn't get it anymore. You always had it in winter months, and then suddenly you didn't have it. And we concluded that the climate was warming, and there wasn't enough cooling going on in the winter for this ice tongue to form. So it's just not forming because it's too warm. And so we thought, oh, well, now we have to go up to the Arctic and study why it isn't there. What's going on in place of this deep convection, this chimney? And so confidently applied for funds, and along with other colleagues from Germany and France, and nobody gave us any money to go there. And I think that when you're dealing with funding agencies, you're often dealing with complete morons. And I think the moronic attitude here was, well, you're not getting chimneys anymore, so we don't need to bother to fund the research in that area anymore. And the question of what are you getting in place of that, what's going on, and where's the heat going, where's the water going, didn't occur to the funding agencies. So nobody's been able to go there and see what's going on since then. So that's just
I have two questions about it. One is, I'm trying to visualize what it would be like. The way you describe it, it sounds like some kind of whirlpool. If you went sailing along, would it go sucking you down into this thing, or what does it look like when you discover this thing? Is it water that goes around in a circle, and if so, is there a hole in the middle, or what?
Well, it does go around in a circle actually, but it's not as violent as a real whirlpool. You can see it in satellite images. You can see it also if you go and out there and put some floats out. You'll see them going around in a circle. But
would the floats? Would anything suck them down if they're going? If it's whirling and going downward, wouldn't it pull something down?
Well, the water itself is what goes down, and that's the reason behind the chimney idea, that it's a way in which surface water disappears down into the deep ocean and then heads off southwards in the deep ocean and comes up somewhere else.
And do you know where it comes up?
Well, some of it comes up in the Indian Ocean, and in
hold on, wait a minute. From the Arctic and Greenland, this water is going to go all the way around South America and then come up in the Indian Ocean?
Yes, it's a worldwide circulation.
Isn't that amazing? Oh, now I've heard it referred to something that sounds like starts with an H. What is the word?
Helium.
Thermohaline circulation. Yes.
How do you spell it? Thermo what?
Thermo and then haline, Haline. So that means heat and salt are involved in how it works.
Okay, now clearly this is something we need to know more about. I can see that would be a nice thing to find out. But what I'm wondering is, when it comes to deciding what the world needs to know in what priority in order to solve global warming, is there any kind of systematic planning going on in terms of saying, would this, for example, the IPCC is going to have their annual Wingding in Glasgow. Now, do they have a meeting where they can say, now look, most urgently, we need to know about chimneys or blah, blah, blah. And so please fund this guy to go and check it out. Is there anything like that going on? Or is it just a matter of people just kind of guessing about what might be useful and what is not so important when they decide whom to fund?
Well, I think the scientists know what's important, but that which gets funded is not the same thing. It's what appeals to the politicians, what the politicians thinks appeals to the people, and what we get done is not necessarily what needs to be done in science.
Well, but also there are lots and lots of funding agencies in the world. I mean, I know Paul Werbos, who was at, NSF, but now let's suppose you apply to NSF for money for a study of chimneys, and Paul applies the same project idea to some place in Sweden. And is there anybody saying, no, you're duplicating efforts? There ought to be some kind of way of keeping track of who's applying for what, so you don't all do the same thing or miss something really important. Is there anything like that?
No, there's nothing organized like that. Everything is a free-for-all, basically, and it shouldn't be, because, as you say, there are certain things which are very important to know about, and other things which we can sort of let go for a while. But the question of priorities is something that is generally, as far as I can see, not addressed by funding bodies or by anybody. People who want to do things just try and make the best case they can that this is important and hope that somebody will fund it.
It's all a very disjointed process. It's like free for all, survival of the fittest. Often only a few projects get basically the biggest part of the pie, the funding pie, and everybody else suffers, right? And also, there's no connection from one country to another country. Also, applying for the funding is a very long and tedious process, and funding agencies do that. They make a lot of hoops, basically, that you have to jump through, which are very time consuming. And therefore, it's not like you can you can spend a lot of effort on a funding proposal and then have it rejected and try to send it somewhere else. But all that takes a lot of time and effort on the part of the scientists. And that's time and effort that they could be spent with them actually doing the research. You think that governments that are saying it's a climate emergency, they could kind of at least have, liaison with other people and make sure that, okay, we've got to fund work in this area, this area, this area, this area. Now, who are the people? And be sort of proactive. If the funding agencies were proactive and they know who the scientists are, so they should go to the scientists and say, look, here's money to do this project. Here's money to do this project, right? It should be done that way instead of being completely up to scientists to just spend all this time doing proposals. And I don't know what percentage of proposals are accepted. I think it's a small percentage that get accepted for, in general for any scientist. That's why you have to have a lot of proposals out there to different funding agencies at any given time to hope, that some get through.
It doesn't take much for even me to say, if this is an emergency, and I certainly am convinced it is, this is exactly what should be done to straighten, first of all, to try to solve the problem. You want to develop a more rational system of prioritizing the questions that you need answers to, and upping the amount of funding that you provide to get the information, and make sure that there's some reasonable way of allocating these funds. So is there any effort being made to try to persuade, let's say, the IPCC to make such a recommendation to the world's science foundations that they should collaborate and coordinate better?
Yeah, I don't think that the IPCC is doing anything at all to those efforts. Maybe at the climate conference coming up in Scotland, maybe that's a good idea for a session.
Yes.
I think that's a very good idea to hold some press conference or session on that very question.
Yeah, it's a good point. I mean, we're in an emergency now of climate. I mean, and a genuine emergency. It's not just one where somebody says it's an emergency and then does nothing. It's a real, genuine emergency, and that means there are things that have to be done now to resolve some problems about what's going to be happening to the world climate. And certain things need to be done and need to be done urgently. But you wouldn't think that was the case when you look at the funding agencies. And IPCC would be an ideal candidate to be a leader in saying X, Y, and Z needs to be funded. But in fact, it hasn't traditionally done that. And the national funding agencies, even the international ones, haven't been doing it. The British funding agency, Natural Environment Research Council, is just utterly pathetic and always has been. But you also have the European Union and that's better. But it's still it tries to prioritize, and I think it is doing a better job than anybody else. There is a prioritization and a sense of urgency about certain fields of science in the European Union, which unfortunately Britain has been so stupid as to leave. But I'm still in it because I'm in Italy. And, the national agencies have this kind of old-fashioned thing of, oh well, think about what we should, what new fields should we think about for next year and the year after, and so there's nothing useful gets done with any sense of urgency. And then if you can persuade a philanthropic agency to support you, because there are agencies around that give out money for science, not in huge quantities, but in quantities that are enough to go and do a research voyage or something.
Okay, well, look, I would think now the next step is for us to build much more of a public momentum, a movement, a public awareness of the urgency of our situation, and then have sort of an outcry, a demand on the part of the public for a more rational system of planning the research.
Well, that is happening. That will happen eventually. It's just a matter,
we don't have the time for eventually. We have to get
but it will. When I say it will happen eventually, it's because the extreme weather events around the world are really hammering many places where people didn't expect things to happen. Like the temperatures in Canada of almost 50 degrees Celsius, the burning down, the wildfires burning down a town in BC, when one sees that in California, when it happens, well, it happens often. We had Paradise just a few years ago, but in Canada, considered a colder place, and somewhere where these events weren't expected to happen for decades and decades, and of course all of the flooding in Germany, in very wealthy neighborhoods along rivers, and that was completely unexpected to them, and the flooding in China, like more and more extreme weather events are wreaking havoc on people, in wealthy countries now, not just in, poorer countries where it's just sort of sloughed off. But, imagine an extended heat wave over, India. Temperatures in India are large to begin with. They always have been. There's always been things going on. But imagine a widespread, heat dome over that country, that knocks out a lot of the power, and there's no air conditioning, and we'd be talking about millions of deaths, right? Deaths on the streets and stuff. I mean, that's just a matter of time. And also, the growing areas of the world, a lot of the US spring wheat crops, for example, have been completely destroyed, and up into Canada and Saskatchewan, Alberta, crop failures. And it's only a matter of time before there's enough of these from extreme weather events that we're going to have global food shortages and probably famine. So this is, these are things that I guess that I would say, are definitely in the pipeline for the next 5 to 10 years. And that's, those are really not stoppable at this stage, I would say. They're going to occur, and they're going to really focus people more and more on climate change, and people are getting, quite worried. Even what I see this year is definitely a noticeable shift in the mainstream climate scientists that would have laughed at things that Peter and I and other people have said, say over the last 5-10 years, even saying, that's very alarmist. You're just alarming. It's never going to happen. And now these people are starting to say, oh, things are really a lot worse than they thought. I'm talking about scientists, the Michael Manns and some of the other mainstream sort of, when I say mainstream, I mean, they get lots of press, they have ins with the world media. And, they're starting to say, well, things are really bad now. But they're also saying, and we've been saying this all along, which is a complete lie. They've been saying the complete opposite and attacking people that have been saying it all along. And now, now they're trying to take credit and say, we've been warning you. This has been coming along all the time, which is complete, bollocks, I think is the British word for it. So, but I mean, so it's a problem. I mean, but as far as the chimneys are concerned, it's vital that we know what's happening with the chimneys and if they are shifting where they're shifting to, because if these things shut off, basically Europe, Western Europe can go into a deep freeze, and the rising temperatures clashing with the colder the cooling because of the slowing down of the AMOC, the Atlantic Meridional Overturning Circulation, or the thermohaline circulation, thermal being temperature, haline being salt, right? Those are vital, and we can expect. I think that clearly, I think the AMOC has already slowed down, and I think that's part of the Atlantic Meridional Overturning Circulation. So the water. Think of the Gulf Stream water coming up off the east coast of the US, going northeast, crossing over to Europe, and that brings a lot of heat in that water up to Europe. And that water cools down as it goes into the Arctic, and it's very salty. So it's both cold and salty, both factors that decrease the buoyancy, or they increase the weight of that water. So then it sinks down in these chimneys that Peter's talking about, goes down to the deep ocean, and then recirculates back up, down, and it's a global circulation thing, and then comes up in the Indian Ocean, right? That whole circulation pattern is slowing down, so Europe will be a lot colder from the Atlantic being, that heat not being brought across, but it's also heating because of climate change, global warming. It's heating on the land a lot more, so the temperature difference is becoming larger, and we're going to see, Europe's going to be just devastated by these extreme weather events. And I did an interview recently with CTV, and they said, my conclusion was that you haven't seen anything yet. They asked me what we could expect in the future, and I just said, well, you haven't seen anything yet. It's like it's just starting. It's just you're just seeing the beginning. So we're in for a huge huge problems in society from abrupt climate change. Like this is it.
Are you saying that the Gulf Stream is already being affected or not?
Yes, it is. So Peter wanted to, I presume, go in ships and measure the water rates, the flow rates going down in these chimneys, measure the area on the surface of these chimneys. Actually you can put if we're lucky enough that an Argo float, right? We've got these floats going around the ocean. If we're lucky enough that an Argo float hits that region, we can get measurements of water salinity and temperature, density, oxygen content, all kinds of things with depth through the water column. But, the chances of an Argo float going in that region are minimal. You have to put, Argo float should be taken to that region and put in the water to study that region. I mean, that's something.
What's an Argo float?
Okay, well, this is a NOAA program, I believe, the National Oceanographic and Atmospheric Association. So they have these autonomous floats, which they basically have buoyancy chambers. It's all automated. It's like a drone in the water. And if it's on the surface, and then it pumps water into the buoyancy chambers to push out the air. It sinks down several thousand feet and collects data the whole way, and then rises to the surface again. And then once at the surface, it sends signals. It sends the data, transmits the data to satellites, which then goes to a central station where it's analyzed. And I think there's thousands of these floats now in the ocean, and they're just carried randomly with the currents of the ocean. Okay,
yes,
so
well, it's sort of French version of these floats that chimneys were discovered because French scientists put in the floats float with neutral buoyancy. That is, they sink to a depth that you want them to sink to, say 500 meters, and then you track them. And this set of buoys that he had deployed were starting to rotate and go around in very tight circles, which completely unexpectedly, and that was how the existence of these chimneys first was revealed. So they're important, but the interesting thing about the chimneys is that they stopped working, and what's going on now? And one of the problems is that the loss of production of chimneys is slowing down the Atlantic circulation. So the thermohaline circulation in the Atlantic slowing down, and you're getting less water coming up in the same direction as the Gulf Stream, because it goes in the same direction, and we're going to have a cooling of Northwest Europe, at least not a warming. The temperature's not going to go up as fast as the rest of the world. So you think, oh, that's great, we're saved from global warming. But the warm water that doesn't go to Northwest Europe stays in the tropical Atlantic, which is where it starts from, and that gives rise to much more intense hurricanes, because the water is now much hotter and that it doesn't flow away, it just stays there. So we expect to get more intense hurricanes, and we are getting more intense hurricanes now than we were getting a few years ago. So you don't get any benefit from these changes. You get a disbenefit in a different place. And so the fear is that there will be really destructive hurricanes now from here on forever, if the thermohaline circulation isn't restored.
Now, where do they happen? They're just, as far as I know, the only hurricanes we hear about are, from the Caribbean up going to the U.S. and Mexico. But there are typhoons in Asia. Are hurricanes? Are there a significant number of hurricanes in other continents, or are we just blessed to have them in North America?
Well, there's typhoons in Asia, yes, but the hurricanes that you get in North America, usually they're in southern states of the US or the Caribbean, Central America. But occasionally you've had hurricanes going quite far north. I think, didn't Canada get a hurricane?
Oh yeah, we get the hurricanes on the East Coast, and some even cross the Atlantic and go up to approach Ireland and the UK. And they're happening. Not only are they larger and more powerful, in fact, they're talking about making a Category 6 because you get some that are much, much stronger than the Category 5 cutoff limit, like from 4 to 5. Way stronger. And if you follow the sort of wind speed change in a given category, we're well long overdue for having a Category 6, and they're actually talking about bringing it in now. I think I mentioned it about 4 or 5 years ago that should happen. But these so it's all connected. I mean, the in the atmosphere, right? The heat the heat movement from the equator to the poles is all being disrupted, because the Arctic is warming so much faster than any other region. So this affects the jet streams, in the atmosphere, slows them down, and they become wavier and stuck. We get all these extreme weather events, and about 2/3 of the heat that's carried from the equator to the pole is carried in the atmosphere, and about 1/3 is carried in the oceans. And the oceans, because of the ocean heating, and those currents are also changing. So the entire way that heat is moved on the planet has been disrupted and is changing. And the ocean part with the chimneys is a vital part of it. So it's absolutely insane that there's not funding to find out all we can. What we expect, I think, with the chimneys is they're likely to, when it looks like they're weakening and disappearing in the Arctic. So there's a couple of possibilities. One is that the water still descends, but it's more over a distributed area, not in a finite area like a chimney. And another more plausible reason is that the chimney will form at much lower latitudes. Okay, so instead of the water going straight up into the Arctic and descending, there'll be chimneys forming at lower latitudes.
How
and that's
wide are these chimneys? Like, are we talking 10 feet across or 100 miles or what?
Well, it's about 20 kilometers across.
Diameter,
Diameter. So that's small by oceanographic standards. That's very, very small, a very tight. Very tight circle, and there's extraordinary things. We didn't really finish resolving the properties of these things before they disappeared, but you don't, in the ocean, you don't normally get features that small and tight that are long lasting. You get there's various water spouts and so on, and short-lived features, but these are. We've measured a same chimney opening and closing and reopening over a 3-year period, and that's really extraordinary to have something lasting that long in and being such a small tight feature. It's something you don't get in the ocean.
But another thing that's very important with them is that the descending water is got hot. There's a lot of dissolved carbon dioxide in it, and of course it's oxygenated water because it's from the surface. So there's a lot of exchange of oxygen at the surface to oxygenate the water, and so those gases, the oxygen and the CO2, are brought down to the seafloor, right, in these chimneys. And the oxygen, of course, is important for life that's down there. There's very little oxygen down there, and the CO2 can be basically it can basically end up in the sediments on the seafloor, and it's a way that carbon is removed from the atmosphere naturally. So with those chimneys stopping, we don't get it. We can have oxygen starvation at depth, and we can also have less CO2 being absorbed into the ocean, into the sediment, so that the ocean sink for carbon decreases. Okay, so
now you're talking about a topic that I have had a recent conversation about, and that is with Peter Ward, who is at the University of Washington as specialist on various previous extinction events and talking about future ones. And his main concern is that the warming of the Arctic, either the poles, in comparison to the equator, that there's less cells that are being created from the differential of temperature, and therefore less turbulence in the oceans, and that we will be having a stratified ocean, where his greatest alarm is
the hydrogen sulfide.
Yes, but also the fact that the bottom of the ocean, which now has oxygen, presumably because of the currents, and he was talking about this thermohaline current, that the disruption of that means that there will be a stratified ocean, a very still, quiet ocean, which will be subject to having a lot of microbes at the bottom producing hydrogen sulfide, which is, of course, the apparently accepted to be now the cause of the previous extinctions, the emergence of this, turning the oceans into swamps, in effect.
Yeah, if you read his book called Under a Green Sky, if you're in a good mood and you want to change that to horror, then just read his book Under a Green Sky, and he's written other books as well. So Yeah, I mean, the ocean warming, the sea surface temperature warming means that the water at the surface is lighter, and normally, wind action the wave action extends fairly deep down. When you've got large waves at the surface, they extend down, 7, 8, an order of magnitude, maybe depth down, and it causes mixing of that region. But a lighter water at the surface means less vertical mixing, which is a problem. And also, the water, with there's less vertical mixing, the water gets warmer and warmer at the surface, and then that warmth extends down, several hundred meters at least, which is perfect for fueling hurricanes, because when the sea surface temperature goes above 26.5 degrees Celsius, then hurricanes going across that water extract energy from the water, and the hurricanes grow much larger and much more intense and much more quickly. And before, once a hurricane goes through an area, the water left behind would be quite a bit cooler. But now the water is warmer all the way down several hundred meters. So it stays warm essentially after a hurricane passes, and the hurricane can stall. And if a hurricane's going very slowly, it used to kind of self-regulate itself in intensity, because it would use up all the hot water, and then it would be over cold water, right? Because it's used up all the hot, so that intensity wouldn't grow anymore. But now that the water is hotter, much deeper down, the hurricane can continue to grow even if it's moving slowly. We see these sort of things, with Hurricane Harvey is the best example. Like, it took about 5 days to go along the coastline and raise, drop tremendous amounts of water on Texas. And then the water on the ground caused this sort of effect where it would re-evaporate and then go back into sustaining the hurricane. And like half of the hurricane was over the water and half was over the land. And it was moving a few miles an hour. And, it took 5 days to sweep through, whereas before, hurricanes would be moving much faster and they'd sweep over the land and quickly lose their energy. So we're seeing they're behaving much differently. And it seems, I mean, it's all of these things are occurring. There's just so many things, it's hard to keep track of them all, but most of them seem to be making, being bad news for humanity,
yeah,
unfortunately.
What's happening now, but there was a different thing happening when Chimneys existed, which was that because a chimney was a rotating sinking cylinder, the density of the water inside the cylinder was the same all the way from the surface to the bottom. So it's maybe 3,000 meters of water depth, all with exactly the same density of water. So you found that it was found that plankton you have high concentration of plankton inside the chimney at all times, including the winter and summer, because the plankton doesn't have to do any work. Normally little bugs have to climb in the water to keep their position in the water column, and they have to do some work. But plankton in a chimney don't have to do any work at all, because the density stays exactly the same all the way down to the bottom. So they can rise and fall without having to do work. And the level of plankton in a chimney is very high at all times of year, including the winter and the summer. That stopped because chimneys no longer exist, and the water's got stratified now. And as Paul says, that everything has now the characteristics of a stratified water mass, and the whole thing about this chimney was it was completely unstratified. It was the only place in the world ocean where the water characteristics of the water were exactly the same from the surface down to 3,000 meters.
And the other thing, the other reasons that we know that the Gulf Stream, this whole system has been slowing down, is that when the ocean current, when the Gulf Stream and ocean currents slow down, they tend to override the continental shelf off the east coast more and go right up far north. So, for example, scuba divers in Maine were noticing that the water was extremely warm as they were doing their dives off the coast. You know, the water was extremely warm down to, you know, easily like they dive down 100 meters or, you know, not quite that far, but 30, 40 meters, 50 meters. And the water temperature at the bottom was the same as at the surface, which they, you know, they all wear wetsuits for their diving because the water is normally cold. That the water overriding that continental shelf has caused the sea level rise off the east, off of Maine and areas like that up into Canada to be among the highest in the world, because not only is the, you know, the water volume increasing from melting glaciers, but the temperature of the water is much warmer there, so it expands, and also the currents are pushing more of the water against the coast. So, you know, we have rises of 10, 12 millimeters per year, you know, about 3 or 4 or 5 times faster than the global average sea level rise amount. And the other thing that we're seeing is because of the reduction of hot water going across the Atlantic, we're seeing temperature anomalies. Some people call it a global warming hole. South of Greenland, there's a big pool, there's a big region there. If you look at global temperature rise, the maps, the distribution of it on the planet, often it's like a blue area south of Greenland where the water temperature is actually has not risen, you know, along with the rising temperatures in the rest of the planet. It's actually gotten a bit colder there, and that's a direct result of, you know, actually it's funny because at the climate conference in Paris, I was talking about that with Jason Box, the Greenland climate guy, and you know, he was saying that cold water there is because of the melting, all the heavy melting from Greenland. And I said, well, you know, I think yes, but I think there's a large component of it that's occurring because of the Gulf Stream slowing down, no longer heating that region. And you know, he kind of looked at me and said, well, he hadn't thought of that idea, but it turns out that idea is actually the main reason why we have this cold area. So that's the direct evidence, direct measured evidence showing that the Gulf Stream has slowed down.
Has everybody agreed that it is slowing down? Because I mean, I've read things warning that it might slow down and watch out if that happens, and guesses as to how long it would take, but I haven't heard anybody. Now, when it slows down, is that, I don't know, is that so bad? Slowing down is not the same thing as vanishing. Well, is it possible that the Gulf Stream will just stop functioning?
Well, it's slowing down. I mean, but the thing is, there's a big chunk of the Gulf Stream is wind driven. So it's just like a normal ocean current. So it's the part that's really concerning is the part that's driven by these thermohaline effects. So there will always be a Gulf Stream, and there'll always be, as long as there's winds to drive it. But it's the changes that are due to these thermal and salinity effects that are really concerning. And there is evidence it's slowing down because the deep water, when the chimneys produce deep water, so the surface water is transferred to 3,000 meters down near the seabed and starts flowing southwards. And in the Atlantic, when it starts flowing southwards, it's flowing past the Faroe Islands, and they've got an oceanographic institute there, and they've been finding really reduced flow of that southward current in the Faroe Islands. So it means that what's driving that, which is the sinking of water from the surface, is reducing itself. It's reducing in strength. So the reduced flow in the Faroe Island current is the kind of evidence that the whole thing is slowing down, and therefore
right. So that's, yeah. So there's all these different lines of evidence. Now, about, I don't know, maybe 8 to 10 years ago, there was a paper that came out that made the claim that the Gulf Stream had slowed down about 15%. And then some other studies after that showed that, it wasn't that high. But I think one of the things is there has been a lot of variability in the strength of the of the thermohaline circulation system. Like there's been variability. Now, often, if you look at the math of nonlinear changes and tipping points in systems, or call them, you cross a threshold and the system tips, or these sort of things. I mean, and the world is quite, very nonlinear place. I always like the idea of when you bend a stick and, if you relieve the pressure, it goes back to this normal shape, but then you pass a threshold and you start tearing the atoms apart, and then the stick snaps, right? That's a good tipping point. Or, the canoe, just tipping in a canoe, is another good example. But so the idea is that, in a lot of natural systems, when you approach a tipping point, there are some warning signals. And one of the warning signals is that there's a critical slowing down of the frequency. So you get these, instead of the system being able to, go up and come down quickly, it's slowing down. So it stays up for a longer period of time. And then so the frequency, you can notice it in the math of the frequencies. There's a critical slowing down. And we're seeing that in the Arctic sea ice, definitely, over the last few years. And we're seeing it also in the float rates in the thermohaline circulation. So these are bad signs. These are signs of saying, the system's getting sluggish. It's not responding properly. It's, approaching a tipping point.
But you don't have any clear notion of where, what the tipping point would be mathematically. What kind of threshold would cause an irreversible change?
Okay, well, I think it's pretty clear if we just look at the sea ice loss. So, as long as there's ice up in the Arctic, as long as the heat going in there is melting the ice, so the temperature stays close to the melting point. But as soon as the ice is gone, then you cross this tipping point, and all of that heat goes into heating up the water. So I always use the example that if you've got a kilogram of ice and you melt that ice with a certain amount of energy, and then you take that same amount of energy that melted that kilogram of ice and apply it just to the kilogram of water that's slightly above 0 degrees Celsius because the ice is melted, then that water temperature goes up to 70 or 80 degrees Celsius. Okay, so now, of course, there's mixing and stuff. I'm not claiming that the water in the surface of the Arctic will go up to those temperatures, but it shows you that it's a phase transition. Like a phase transition, solid to liquid is a highly nonlinear transition, or from liquid to gas. And we're getting this exact phase transition, when we lose the sea ice in the Arctic. So when we lose the sea ice in the Arctic, that's when everything starts to change. And we're rapidly approaching this, I call it the blue ocean event, is the term I started calling it, many, many years ago. And we're rapidly reaching that point. And when there's no ice in the Arctic in a September, for say a few weeks or a month, right, the very first year of this blue ocean event, then there's so much more heat being absorbed in the Arctic that the ice doesn't form as much. And then within a few years, instead of just being September ice-free, it's very likely that it would be ice-free for August, September, October, and then a few years after that, July, August, September, October, November. And within a decade, I would say there's no sea ice in the Arctic year-round. Now, many people scoffed at this idea when I first started talking about it years ago. People, they just said there's no way it can happen. The ice will always form in the winter.
I want to know whether Peter scoffs at you because he's the Iceman.
No, yeah. People have scoffed at me over the same thing. And in fact, I've been accused of being an alarmist, a well-known alarmist. Yeah. In fact, there's there's a really villainous, evil, slimy slug of a politician in England. I better not name him, but he was the one who, when I was on television talking about this ice disappearing, said, I'm just a well-known alarmist, and all these satellite pictures that show the ice disappearing were concocted by the BBC. They were faked. And this guy is, he's a loony, and yet he's just been appointed to a government committee on climate change, in which he'll be advising at the time of the COP meeting. So that just shows what kind of clowns we have in the British government. But as Paul said, there are other knock-on effects which come from this ice disappearing, and one of them is this fear of a methane outbreak, because the methane in sediments in the Arctic Ocean is held in place by permafrost, which sits on the seabed and has been there since the last ice age. But as the climate warms and the sea warms, and as you don't get ice there anymore, that permafrost actually starts thawing out, and once it's thawed out, there's nothing to protect the sediments from turning themselves back into methane and just coming out into the atmosphere. Because
you see, you've already persuaded me of that. And in fact, I had a good month or two of being panicky because of methane. And then I met this other guy, Peter Ward, who wants to make me panic about hydrogen sulfide. Now, I've got two things. And the question is, you guys are vying for my attention. Who's going to scare me the worst? And I really don't know which is more ominous. But you said just before Paul joined us, you said you don't quite believe in the hydrogen sulfide theory. So I think maybe what we need is to have a conversation with you and Peter Ward about hydrogen sulfide and methane. See if you can persuade him that the real problem is the methane, or if he can persuade you that the real problem is hydrogen sulfide. How about that?
That's perfect.
Yes,
yeah.
Perfect.
Yeah.
Set
up the session. Yeah.
I'll be happy to set it up. Are you willing, Peter?
Yes.
Okay. Okay, that sounds good. Now, what I'm wondering is also about the psychological effects of this. I am so glad that you said it's really important to be an alarmist, because I quite agree with you. If we don't scare people, they won't take action. And I think that some of the things that are beginning to scare people may indeed change public opinion a little bit, or enough to sort of push people into becoming more insistent on doing something. The wildfires, I would say, are largely that way. About a few months ago, I read an article in the New York Times Magazine, and I generally think the New York Times has reasonably good sense, but it was the stupidest article I think I'd ever read, because it was a long article saying how lucky Russia was that the north was warming, because it's going to melt all the permafrost, and all of that permafrost is going to allow them to use all of that wonderful land now for agriculture. And aren't they lucky, because they'll be able to have bumper crops in Russia. And I thought, my God, don't you have any idea what will happen if all that permafrost melts? And but that has been more or less the position of the Russian government, and certainly a public opinion in Russia. I just did a talk show yesterday with a friend of mine in Moscow, and I brought this up again, that the Russian public opinion, and certainly the government's opinion, as far as I can tell, has been really behind even public opinion in the West, and God knows we're bad enough. But that now there are these huge wildfires in Siberia. There's one going on that's the size of Rhode Island, as I understand it, and apparently for the first time, some of the people who had been excited and thrilled about the melting of the permafrost are now beginning to say, yes, it looks like there's a downside to all this warming. So maybe we'll get some changing public opinion enough to make a difference politically. What do you think?
Well, there was an agreement actually just announced yesterday between the US and Russia on methane and research on finding ways to get rid of methane. I just have to excuse myself. My wife's ringing on the bell. She hasn't got the key, so.
Oh, yeah. Okay, fine.
Yeah,
well,
go ahead. Yeah, I mean, that's one of the things people said about northern countries like Canada and Russia. They talk about the benefits, but yeah, I mean, there's no real any benefits to any country would be very short-lived and very temporary, and then soon be overcome by some other catastrophic event, like the we're finding that with the fires, and also in order to grow crops in the far north, you need good soils, and of course the soils in the north are acidic and very, very thin. They're very poor soils because it's just you have a lot of coniferous trees, and the needles and stuff that do fall to the forest floor or make the soil very acidic. And there's not many. It's not like a deciduous tree that loses its leaves each year, and those leaves then can grow up the soil base, which is what happens, further south. And also, the whole of North America was glaciated pretty much, except for some areas near Siberia, and that scraped all the soil off the rock. So, North American soils are extremely young and generally extremely poor. So, no, I mean, we're going to, I said that we're going to have global food shortages and famine. I mean, we have to really go heavy into things like vertical farming and indoor farming and all of these other things to have, to have any chance to, have enough food, because, crops it's too hot. Like crops in North America out west have withered in the fields this year. Completely, the farmers, it's a waste of time for them to even send their combines out, because these crops have just withered and died. It's just too hot for them.
So,
okay.
Let's just say the Russians agreed to work with the US on methane problems in the Arctic yesterday.
Now, what's the idea? What are they going, you say they're going to try to find ways of controlling it or something? What's the general plan?
Well, it's how to get rid of methane pollution of the Arctic, how to reduce the amount of methane coming out of permafrost. And up to now, they've been absolutely unhelpful, because the people who have been trying to study methane in the Arctic, on the Arctic seabed, for instance, have to really work against the Russians, who really don't want anybody up there doing anything, because their economy is so dependent on gas, and so you don't want anybody upsetting your gas supply by sort of saying, "Hey, look, we got to do something about this." But
about the methane, yeah. So it's not a coincidence, yeah, that some of the top Russian scientists, looking at methane, are Yermanov, Shakova, many others. They're in Alaska working at Alaskan University, right, to do their research. Yeah, so but now, it's not coincidental.
They'll be allowed to actually work in Russia.
Well, that's good news, and maybe results of some of the wildfires alarming people. I don't know. Anyway, thank you both. Time's up, and I'm going to try to set up this thing with Peter Ward so you guys can kick that around a bit, if you're willing. Okay.
Sounds good.
All right.
Go for it.
Thank you so much. Okay. Carry on.
Okay. Thank you. Okay.
Bye.
Goodbye.
Bye.
Bye.